Hi, and welcome to another video in this series about probability theory, the logic of science by Jaynes. This video will be about chapter 9, which is called Repetitive Experiments, Probability and Frequency. In many ways, this is kind of a chapter that we've been building up to in the course of this series. And we started off the series talking about the controversies surrounding the definition of probability and the kind of historical disagreements about what probability ultimately is. And we've mentioned a few places along the way the kind of most dominant interpretation of probability, which you'll see many places, and that's the kind of frequentist interpretation of probability. So that basically says that probability comes about or has to do with fundamentally the frequencies with which things occur of one type or another over some long string of repeated trials or iterations, however it's defined. And I think that we have gone a long way to build up basically our theory of probability that includes much more than that. So we've made the argument that we want to be able to do things like assign probabilities to a hypothesis or a parameter having a particular value, and things that really have nothing to do with a frequency interpretation. Okay, so we have an idea of probability just as an extension of logic, a kind of quantitative statement about the plausibilities of certain propositions. And we've seen that that gives us a very kind of solid foundation to do things like hypothesis testing and statistical inference. But I think we have to acknowledge that there is something very compelling about this frequentist interpretation and the idea of frequencies. So really the goal in this chapter and the next chapter is to show how these problems about frequencies are kind of already incorporated in our logical theory of probability, and just to kind of understand the nature of that correspondence. So to say, where do our ideas actually kind of overlap with the frequentist ideas? And the reason that this is, something that we really want to do is that, first of all, we know that for many people, probability just sort of is fundamentally about frequency. So we want to kind of show how that's already included in our definitions. But more to the point, I think, these frequency ideas, they do come up all the time, and definitely, if you are using probability to do things like analyze gambling games, and you think about probabilities in terms of frequencies, you'll see good success by analyzing probabilities that way. So if you were, a professional poker player or something, and you were trying to understand probabilities of different hands, or what decisions you should make under different circumstances, and you went about that kind of in a frequentist way, you'd get to numbers that would actually perform quite well. So what we kind of want to do is just assure ourselves ultimately that we're going to get the right answers for these kind of frequency problems, and using our probability as extended logic, we're going to be able to deal with situations where maybe probability really kind of is about frequency in some sense, and we just kind of want to make better sense of what those situations are going to be. Okay, so like I said, that's going to be basically the substance of this chapter and the next chapter. So this chapter deals with these topics kind of at a general level, and then the next chapter, chapter 10, is really going to be about the physics of random experiments. So in particular detail, we're going to talk about coin tossing from a physicist's point of view, and we're really going to get into the question of, all right, why, based on our knowledge of physics, would we assign equal probabilities to the two sides of a coin coming up when you flip it? So basically, by the end of that, I think we'll have a very solid example of this kind of frequency theory worked out and shown how our ideas apply to it. Okay, so that gets us up to the end of kind of part 1 of the book, and we've done some of the material from part 2, and I think that's a good kind of arc of this whole controversy about probabilities, whether it's in terms of frequency or plausibility, and we'll kind of get up to I think a pretty stable, complete resolution to that by the end of part 1. Okay, so basically the idea then is, as I mentioned, that we're going to try to understand what kinds of problems and situations will lend themselves to a frequency analysis, and where our ideas of probability will kind of play back and forth with the ideas coming from the frequentist school of thought. So what Jaynes kind of suggests here is that frequency problems are, in some sense, a subset of all problems that we can deal with using probability. And so the whole question is going to be about, all right, well, what subset is it? What kinds of information would we have to have for a problem to kind of lend itself to a frequency analysis? And in what sense is that just kind of a special case of our Bayesian probability as logic? So the general kind of framework that we're going to think about for this chapter is what Jaynes calls a repetitive experiment. Which is the kind of thing that, in the frequentist school, we would talk about all the time. So the idea here is you have some experimental setup, you have an apparatus for doing an experiment, you have some kind of procedure that you're going through, and whatever it is, and you do that experiment, you get some result, and then you do it again and you get a different result. Okay, so if it's like flipping a coin or rolling a die, then you kind of keep track of the numbers that you get or the outcomes of the experiment. And in the frequentist model, what they would take as the kind of definition of the probability of any one of those particular kind of end states of the experiment is just the limiting frequency with which you would observe it in a succession of a very large number of trials. Okay, so you flip the coin, millions and millions of times. Whatever proportion of heads comes up is the probability, and we'll just kind of assert that that thing converges to some limiting value, and we'll define the probability to be that value. Okay, so right off the bat, I think there's kind of a fundamental logical problem with that that Jaynes mentions, and that's that if these experiments are supposed to be so the same from trial to trial, right? So if the assumption is we set everything up identically and we did our procedure exactly the same way and we just record the outcomes we get, then why is it that we get different results at all, right? So evidently, there must be something different from trial to trial if we do the experiment more than once and we get a different outcome. Okay, but in the frequentist theories, it's never really clearly articulated what things are varying from iteration to iteration, right? So if you flip a coin, we know that, well, which side the coin lands on is going to depend on, the kind of initial conditions of that experiment. And the assumption is, well, we're supposed to be holding things constant, but evidently some of those conditions must be changing. So which is it? Is it constant or is it changing? And so Jaynes basically kind of, goes into this and says that it's kind of a fundamental logical issue with the frequentist interpretation that the randomness is just kind of put off to this physical system, and we don't really have a clear acknowledgement of what things are allowed to change and what things are being held constant. Okay, Jaynes tries to make this a little bit more clear by separating basically the things that we do hold constant with maybe the things that are not held constant but are allowed to vary. Okay, so what we're gonna think about in any kind of repetitive experiment situation is that we first have maybe some systematic factors. Okay, so we have, a fixed experimental apparatus. We built some equipment to do an experiment, however it's constructed, and we're doing, a particular thing to it that is something we have control over. Okay, so that might be, we roll the die. Okay, so we know what it means to roll a die. We can kind of see, yes, we did that, or no, we didn't do it. And the degree to which we have control over these things and we can preserve them as constants from iteration to iteration will make them systematic. The other things that might be systematic and held kind of constant from iteration to iteration are things like the physical properties of the objects in the experiment. So, if it's the size and weight of the die that we're rolling, or the table that we're rolling it on, or whatever it is, those things might enter into it, and again, we'd treat those as systematic. Or indeed just the kind of laws that govern the relationships between different quantities. So things like conservation of energy or momentum, or whatever physical laws are kind of applicable to the situation we're dealing with. Those things will be all kind of thought of as systematic factors. Okay, so these are going to be, just to summarize a few of those things like the apparatus of the experiment, physical parameters, or laws, physical laws, or procedures, or anything that's kind of controllable and fixed. Okay, the contrast to this, which is going to be what's variable from experiment to experiment, is usually what people will call the random quantities. But Jaynes actually, I think, has a better terminology for this. He calls it the things that are irreproducible, and specifically irreproducible by the experimental technique that we are using. Okay, so I think it's just to emphasize that, maybe if we designed the experiment a little bit better, or in some other way, we might actually be able to control some of these factors that we think of as uncontrollable, okay, or variable. Okay, so basically the fluctuation or the variability, the variability in whatever other factors are kind of left over that aren't held constant from trial to trial, this is what's going to account for the different results that we get each time we do the experiment. Okay, so the whole idea is that upon performing some large number of these trials, we've controlled for all these things and we've allowed these things to vary, and so we get different experimental results. Okay. And so this might be things like, let's say, the exact conditions, particular velocities and positions of the various entities involved in the experiment, or just things like noise, thermal fluctuation, or electrical noise, if it, depending on the experiment. Any of these things that we don't have control over, and even if we wanted to, we could not reproduce exactly. Okay, so this is what Jaynes suggests basically is what's captured by this idea of randomness, and is really what we should be thinking about when we talk about chance variation and getting different results of different experimental trials. Okay, so the whole question is going to be, all right, how do we start assigning probabilities then to these experimental outcomes, and what do we say about those probabilities based on the frequencies of events that we observe? So again, in the frequentist school, the probability would be defined as the kind of frequency of observation, and we're basically going to ask that question in a slightly different way and say, okay, what do our probabilities predict, and then what do we learn based on what we observe? Okay, so just to kind of fix, again, some of the terminology, and to make the notation, kind of as clear as we can, the number of states, let's say, that the experiment can generate or terminate in okay, basically whatever we can kind of get out of the experiment as our data, we're going to call that number little m. Each iteration that we do of the experiment, each time we do it and we get one of these kind of states coming out, we're gonna call that a result. Okay, so just so we have a clear name. A result is what happens when you do the experiment and it falls into one of these little m distinguishable outcomes. Okay, there's kind of a subtle point here that, you know, depending on the experiment, m may be either kind of obvious or it may be a little bit subjective, or it may kind of be unknown to us. So we're going to assume, kind of for the sake of argument, that we know what this number little m is. And for some experiments like, you know, rolling a die, that's going to be pretty obvious. So this, you know, m for a dice roll would be 6, because we can sort of imagine that each one of the 6 faces of the die could come up in the experiment. But if it were something like, you know, we were doing a medical experiment and we were treating a number of different patients with, you know, some treatment, this number might be the number of distinguishable reactions that the person has to the treatment, and in that case, you know, we may have to make some kind of arbitrary judgments, or it could be something like you know, the number of species that can evolve in, you know, a certain situation, in which case we may not know it going in, so we may kind of think we have a handle on all the possibilities, and then we may observe a new one and may kind of change our whole kind of thought structure. Okay, we're not going to dwell on this too much, but just to kind of emphasize that even this number m comes to us through some amount of prior information that we bring to the problem, and it may just be, you know, kind of manifestly obvious from looking at the experiment. Okay, so each time we do it, we get a result. If we do the experiment as a whole, okay, so we're going to repeat this like a number little n times. Okay, so little n is the number of times we're going to go through it, and those all those results taken together in those little n iterations is going to be called the outcome of that sequence of experiments. And basically, we can think of any outcome as an n tuple. Okay, so an ordered list of n numbers that are taken from this set of size little m. So we'll basically label the states of this experiment 1 through m, and we'll imagine that we're doing it n times. So we're going to have basically ordered n tuples, r1 through rn, is going to be one particular outcome of the experiment done n times. Okay, hope that's all kind of clear, but again, just to kind of fix some notation. So when we talk about probabilities and frequencies, then we basically have to kind of make a distinction between which things we assign and which things we're measuring. Okay, so for us, probabilities are going to be things that we assign based on a state of knowledge. Okay, so these are going to be numbers that we come up with based on, you know, conditioning on some background information or some working hypotheses about, you know, the mechanism of this experiment and what kinds of outcomes we might get. And we can ask that question in many different ways, and we'll see some of them today. But anyway, the point is that the numbers we come up with are going to be assigned, and they're going to be based on our state of knowledge. Okay. In contrast, we might sort of just ask the question, all right, what are the frequencies? Like, what do we mean by frequency? And that's just going to mean, well, whatever we get by doing the experiment and tabulating the results, you know, however it's defined, maybe how often did we get one result or another in a particular outcome. So these are going to be things that are measured, right? And do not depend on our state of knowledge. Okay, so the fundamental difference, and I think this is kind of what separates our way of thinking from the frequentist school, is that frequencies, we will kind of admit, happen in the course of doing experiments. Okay, we'll freely accept the fact that, yeah, you hold something systematic, there's some things that aren't really controllable, and when you do an experiment multiple times, you're going to observe different results. And if you tabulate those results and calculate frequencies, in many situations they're gonna stabilize to some long-term levels. And those are all things that we can kind of measure, and we admit that it has nothing to do with how much we know about the experiment or not, or how much we know about the experiment, whether our knowledge is kind of correct or not. It doesn't enter into it. They're just kind of physical quantities that come up in the course of doing the experiment. Okay, probabilities for us are a reflection of the things that we know and don't know about either one of these categories of factors. So either our kind of assumptions about physical parameters underlying the problem, or kind of the sorts of variability of the things that we're not able to control in the experiment. And we might have kind of probability models that come out of that, assignments based on various rules of probability, and those are all dependent on our state of knowledge. Okay, so the real kind of fundamental question, the way that Jaynes frames it here, is what kinds of knowledge, sort of in what states of knowledge would we have to be to get, what kinds of knowledge produce probabilities that are equal to the frequencies. Okay, so frequency is something we can measure, probability is something we can assign, and the question is, all right, well, in what situations would these things overlap with each other? And one of the big kind of categories that just kind of suggests itself right away is, well, if the only thing we knew about the experiment were the frequencies, then that's probably what our probability assignments would be, and so it's natural to expect there would be a correspondence. Okay, so we're going to get into this in a little bit more detail. Okay, but really the question is going to come back to what kinds of prior information are we thinking about conditioning on? So at one extreme, then, which is, it seems kind of silly, but it actually turns out to be a useful thing to look at, we're going to consider what Jaynes calls the poorly informed robot. Okay, and what we mean by the poorly informed robot is the probability robot that only has the background information, which we'll call I0, that there are m states and n iterations. So basically that there are m to the n possible outcomes. And this number, m to the n, we'll call capital N. So capital N is the number little m to the n. And we're just going to tell the robot, basically, in this configuration that we're talking about, the number of things that can come out of it is little m to the n. All right, each state n times. And as far as the robot is concerned, it doesn't know if that's n iterations of an experiment with little m states in it, or it might think that this just one iteration of an experiment with m to the n states in it, or it doesn't even really have any idea where these numbers are coming from. It's just basically thinking of them as ordered n tuples, which you could also write as kind of digits base m of a number that's n digits long. And so the robot just has that kind of single piece of information. All right, so naturally then, what it's going to say if we ask it for the probability of any one of these particular outcomes. Okay, so let's just say, what's the probability of an outcome R1 through Rn, conditional on this very, very limited background information? Well, it knows that there are m to the n of these possible things. It has no information to prefer one over the other one. So it is what we described as indifferent to the different propositions. So that means that they're all going to have equal probability. Okay, these are mutually exclusive exhausted propositions. There are capital N of them. So it's going to be probability 1 over n for any individual outcome. Okay. If we asked it for probabilities of sets of these things, right, what we'd call an event. So let's just say we want the probability of some event A, which is a subset of all the possible outcomes. The probability of that in this kind of very ignorant, poorly informed robot's estimation is just going to be what we call the multiplicity of A, okay, which is the number of outcomes that correspond to that event. Okay, so this is kind of the usual treatment. And with the notation we'll use for that multiplicity of A, we'll call M n of A. So capital M, multiplicity, n is just to remind us that we have n trials, and that's the event A. Okay, so we're going to need to be able to count up things like the number of ways different events can happen. Now let's do just an example to make this hopefully a bit more clear. Okay, so we mentioned, so let's say that we're doing a die roll. Okay, so that means that we have 6 possible states, right? 6 outcomes, or 6 results that the die roll can produce. We assume that we do it n possible times, so this capital N number is going to be 6 to the n. Let's say that we wanted to ask the poorly informed robot, what's the probability that the first die roll that we get is a 1? Okay, so what is that? It's the multiplicity, sorry, I said this wrong over here. Probability is going to depend on the multiplicity, but of course we have to divide by the total number. Okay, I forgot to mention that. Okay, so again, we count up the number of states, and then we divide by the total number of states, and according to the principle of indifference, we get that ratio as the probability. Okay, so what's the multiplicity of the event? The first die roll is a 1. Well, we're considering all the possible outcomes, which means all the possible sequences of dice rolls. If we fix the first roll at a 1, then we have 6 to the n minus 1 remaining die rolls that we can consider, and we have to include all of them because they're all in our universe and they all have that single property that we're interested in. All of those taken together, that's then the multiplicity of the event that we're talking about, and we divide by the capital N number, which for this setup was 6 to the n. Okay, so do some cancellation and we get 1/6. Okay, so not a big surprise, but you can see how it works out that in the situation of kind of perfect symmetry and ignorance, we'd assign equal probabilities to the 6 results of the first die roll, and we'd get a probability of 1/6 for each of them. Okay, if we then wanted to ask something like, let's say a conditional probability, maybe the conditional probability that the second roll is a 1, given that the first roll was a 1 and this background information, okay, well, what's that? By definition, that conditional probability is probability of both of them being a 1, okay, conditional on background information, divided by the probability of the first one. Okay, that's just the product rule of probabilities. Now, what is probability of first die roll being 1 and second die roll being a 1? Well, same kind of argument as before. If we fix the first 2, we have 6 to the n minus 2 remaining. Okay, possibilities for the rest of the dice rolls. We have to divide by our multiplicity, which is, by our total number of outcomes, which is 6 to the n. Okay, all of that now divided by what's probability of R1 equals 1. That's what we got before, that's a 6th. Okay, so again, we get some cancellation. 6 to the n minus 2 divided by 6 to the n, that's just 6 to the n minus 2. And we have that divided by 1/6. Okay. So that's going to be, again, a sixth. Okay, 136 times 6 equals 1/6. And what's interesting about this is it's the same probability that we would have gotten if we just asked the unconditional probability for R2, not conditional on R1. Okay, so what we'll actually see after kind of extending this a little bit and sort of thinking it through is that any two roles that we're interested in, okay, let's say Ri and Rj, for any pair I and j, these things are independent, conditional on I0, let's say for any I not equal to j. Okay, so again, not too surprising, but again, you can think it through just by saying that this robot, it has no knowledge of what's going on. Okay, this state of background information tells it nothing about any connection between these different dice rolls, and so it's not surprising that it would assign equal probabilities to all possible outcomes of individual dice rolls, and that those probabilities would be independent of each other. Okay, so it's not going to make any kind of inference from one die roll to assign probabilities to another one, because as far as it knows, they're completely disconnected from each other. Okay, so what's interesting about that, or kind of what makes that a little bit disturbing, is that this robot, well, first of all, it seems to be getting the right answers. Okay, so that's a little bit weird. So, we know that if we ask the same question to someone who was doing kind of dice gambling for a living, and someone who knew lots about dice and dice rolls, we asked, okay, what's the probability of getting, a 1 on the first roll? They would give us a 6, and we'd ask, what's the conditional probability of getting on the second roll? They'd say it's independent, and the probability is a 6th, and we'd certainly agree with them. So it's a little bit weird that, we, knowing lots about dice and their physical properties and kind of independence of dice rolls, end up with the same statements of probabilities as this poorly informed robot that knows absolutely nothing about dice and just has this one bit of information that we kind of programmed into it. And we'll come back to this when we talk about coin tossing, but basically the point here is that it's okay that we end up with the same numbers despite having very different kinds of states of background information, because basically what we'll see is that our state of background information includes lots of assertions about the symmetries of this situation and the kinds of variabilities that come up and produce different results, and it just ends up producing probability assignments that are the same as a perfectly ignorant robot that doesn't know any of that stuff. Okay, so Jaynes says something to the effect here that an idiot might guess at the same conclusions that a scholar takes years to come up with, or labors for years to produce. I can't remember how he says it. And that's okay. It just means that we ended up in the same place, but we came at it from a lot more information. What's kind of more interesting about it, I think, is that we actually, secretly in the back of our minds, we probably have some other alternate hypotheses that might get revived under some conditions that this poorly informed robot would just have no reason to be concerned about. Okay, so imagine, if you will, that we were doing this experiment and we were kind of rolling an actual physical die and doing it a large number of times. But suppose that we actually got the same results, I don't know, maybe 10 times in a row. Okay, so our first die roll, our second die roll, our third die roll, we did that 10 times, we got 1, or maybe somebody's doing it, so we're not necessarily too implicated here, but we're watching the experiment, we see 10 dice rolls in a row, and they're all 1. Okay. The poorly informed robot thinks that's fine. It has no basis from which to conclude anything. It's just continues on its merry way and says, okay, well, further results are all going to be independent and have probability of sixth. But we might actually be led to do basically a little bit of inference here. Okay, so upon seeing kind of a very unlikely result like that, we might start to consider alternate hypotheses that would affect our probability assignments. Okay, so the point here is that we might do some hypothesis testing, or what in more general senses we would call induction. Okay, so induction, generally speaking, means drawing inferences from some particular observations to more general assertions or statements of fact about the things that we're observing. Okay, so we know that induction is something that we are capable of doing, right? We do it all the time, but according to the poorly informed robot and this strict assumption of, or this kind of fact of independence of the trials that comes out of kind of perfect ignorance of any kind of logical connection between the trials, there's no such thing as induction, right? So basically what we're gonna need to ask is, well, what logical connections might we make between the different trials that would allow us to do any of these inferences? Okay, and all of that is going to be part of our background information. So maybe at one extreme, if we had something like, background information I1, which is that we know for a fact that the die is fair. Okay, and by fair we mean, perfectly symmetric, or at least as far as we're able to measure, perfectly symmetric, and it's got the right numberings on it, and we've measured it and weighed it, and it's a well-constructed die, and it's being tossed in a fair way and in a manner that we accept as being fair and kind of subject to all of the chance variability that we're accustomed to in thinking about dice rolls. Nothing fishy is going on. Well, based on this event up here, which let's just call this A, the event that we saw a sequence of 10 ones in a row, well, we might actually conclude that our probabilities are unchanged, right? Maybe for the next roll, condition on that, we might continue to think that it's a sixth, although we might start to doubt ourselves a little bit. But anyway, if we condition on that background information, which I should put in there, I1. Our conditional probability is going to continue to be a sixth, okay? Because we're going to basically assert that through physical symmetry, right, we have some positive knowledge of the die that prevents us from reaching any kind of other inference about the next roll. Okay, if we had, let's say, a state of background information that the die could be a trick. Okay, so this is kind of like what we saw in the example of the magic trick. So, if we're aware of the existence of things like loaded dice or, dice that have the same number printed on all six sides, if we think there's any kind of chance that that might be going on, or that, the person rolling the dice isn't kind of doing it right, then we might kind of start to infer some other things. So maybe, based on that background information, we might get to a number that's greater than a sixth. Okay, so at one extreme, I think Jaynes mentions this, that if we kind of knew for a fact that it was a trick die, and we just didn't know in what manner it was a trick. So maybe we know that it's the kind of die that has the same number on all six sides of it. Okay, we didn't inspect it very carefully, and we just know that it's like one of those silly dice that has the same number on it. Well, once we see a single one, then we know which one of those dice it is. So the only kind of mystery is, all right, is it an all one die or an all two die? After we see one, we know that it's the one die, and so we would actually conclude that the probability is now, that this event is certain, that the probability is 1 of it coming up 1 the next time. Okay, if we go kind of another way, and think about, well, maybe we can imagine, having some background information that the die that we're rolling actually produces some fixed proportions over, let's say, the next 120 rolls. Okay, so however it happens, don't know exactly how this would work, but maybe it's kind of an assumption that we have that through some concealed inner mechanism, it is the case that when you roll this particular die, you get equal numbers of 1 through 6 over the next sequence of 120 rolls. Well, actually now, seeing that we got 10 of the kind of 20 possible ones in the first 10 might lead us to conclude that this probability is now less than a sixth. Okay, because we've kind of used up some of those in the first 10 rolls, and there are fewer ones now remaining. And this would be basically reducing us back to kind of a sampling without replacement problem. Again, if we assume that there's kind of nothing going on that would give us any linkage between successive dice rolls other than the number of remaining possibilities, then we might get a sort of m minus 10 over n minus 10 kind of number, as we've seen in the sampling without replacement. So, okay, it's not really important to go through kind of all the possibilities here, but I think Jaynes makes the point that because of the possibilities of these different kinds of background information and the different kinds of inferences that we would draw, or inferences that we would make based on that prior information, there's no kind of universal rule for doing induction and kind of generalizing from the particular to the general, or drawing conclusions from the particular examples to the general. I think just the essential point there is, okay, it's not, there aren't universal rules for it, but we know that we're able to do it. And there must be some kinds of guiding logic that we might have in a particular problem that would allow us to do induction of a particular sort. Okay, so it's all going to be kind of case-by-case basis based on the background assumptions that we make in that problem. Okay, and he basically says something that to the effect of, if all you think about is frequencies, right, and you're sort of stuck in this frequentist model of probability is just about frequency from independent trials, meaning that you're always kind of assuming that the trials are independent, you don't allow for any kind of logical connections between trials, then of course you're not going to be able to understand or account for induction because you just have no mechanism to do it, right? So the poorly informed robot that continues to think that all trials are independent no matter what observations you make, that robot won't be able to do induction, and neither will someone who thinks about probabilities in terms of frequencies. But in our way of thinking, kind of where we're going to go with this is to say, well, for some states of background information, the trials are actually not independent. We can break that independence assumption, meaning that we have some logical connection between the trials, and therefore, yes, induction comes about quite naturally because each time we make an observation, we update our probability assignments for the next round of trials. Okay, so the example that Jaynes points to here that just kind of indicates that this is something that we actually do all the time is survey sampling. Okay, so if we think about what happens when we do a survey sample. Okay, so we are, maybe we're interested in people's opinions, let's say, about some upcoming proposition that's going to be voted on, and we do some poll of the population, some number of people, and we get results like 67% of people support this measure, then we know that we would kind of conclude that 67% about of the population support that measure, assuming that we did the sample kind of in a reasonable way. So on what basis are we making that inference, right? And if you believe that, you think like the poorly informed robot, you would say, well, there's no basis for that inference because whatever result you got for each person has nothing to do with the results you're going to get for the population at large or any other particular individual. And so, you don't have any basis to make an inference from a sample to the population. Okay. In our way of thinking, what we'll say is that actually we do have some prior information, which is that we're dealing with a population that has a fixed proportion, say fixed proportion theta, let's call it, that support, let's say, fixed proportion who would answer whatever this proposition is, who support it. Okay, that proportion may be fixed, but it is unknown to us, right? We don't include any other information in our background assumptions about what that proportion is. What this means is that the events that that the ith person we survey gives us a yes response to the polling question, and the jth person answers yes, those events are now not independent. Okay, of course they're not, because if we do a sample of, let's say, one person and we get a yes vote, then that changes our kind of posterior probability assignment to this parameter theta. Right? So this basic kind of parameter estimate, the kind that we've been doing. Right? So maybe we would start life with something like a uniform prior. Okay, so if we started with, let's say, just a uniform prior for this parameter theta, okay, just as we've done before, and then let's say we did a survey and we got a yes vote. Okay, we're interested in things like maybe what's the probability that the first person would answer yes. Okay, if we condition on any particular parameter value, we'd get that probability is theta, again, assuming some things about the way we do the survey. So then the question is, all right, well, if we condition on assuming that we did get a yes value, we can ask the question now, okay, what does our posterior probability distribution for theta look like, given that we got a yes value? And that would be just the normal way that we've seen it done. So, well, first of all, this is the probability for any particular value. Maybe I should have done this in another order. But the probability that we get a yes, now not conditional on that, we would say is the integral over all these possible thetas of theta, the parameter, times its prior probability distribution. Okay, prior probability distribution of theta, d theta. That prior we assumed maybe was uniform. Okay, so that's just theta d theta. Integral of that is 1/2 theta squared, 0 to 1, so that gives us a half. Okay, so without knowing anything, right, we can still come to a probability assignment, which is that we'd say, well, the first voter giving us a yes or no answer to the poll is going to be a half because we sort of don't have any information on the parameter and we have to integrate over it kind of in total honesty. But we end up with that kind of symmetric result. Now the question is, all right, if we did observe it, what's our posterior probability assignment? So that's going to be whatever our particular data likelihood theta is divided by the total probability. Okay, just as we've seen in parameter estimations, that's going to be 2 theta. Okay, so basically it's a different probability distribution than what we started with. Okay, so we start with the uniform distribution. We end up with something kind of weighted more towards the yes end of the spectrum, so with higher probability kind of for values closer to 1. And then that would affect our forward-looking probabilities about, say, the next person giving us a yes vote. So I guess the point here is, and it's a little bit of a subtle point, but to put this in terms of the differences between probabilities and frequencies, in a situation like this where we assume that there's some fixed proportion, right, but we don't know what it is, I think that the frequentist answer to the question would be basically we don't know the probability, right? So if we ask the question, all right, what's the probability that the first person we poll gives us a yes vote, the frequentist answer to that question will be, well, whatever that probability is, it's fixed, but we don't know it because we have to, in order to know it, we have to do the experiment and look at the long-run frequencies as we poll more and more people. Okay. For us, we would say, no, we can answer that question. We can get to a number, which is a probability assignment for that event, and the point is that the probability is a reflection of what we assume that we know and don't know about the problem. Okay, so this is kind of the subtle difference that I think in the frequentist model they'd say the probability is some physical property of the system you're measuring, whereas we would say the probability is our state of knowledge, or comes from our state of knowledge, and we can always answer these questions like what's the probability of X and Y. And depending on the kinds of information that we assume we condition on, these events might be independent or they might be dependent. Right? So we may be in a situation like where we've assumed that we've conditioned on kind of all of the systematic factors, and all that's left are things that seeing one result tells us nothing of use for predicting the next one, in which case fine, fair enough, and those probabilities might be independent. Or it might be the case that there's some systematic factor, like this parameter theta in this problem, that we know is fixed and influences the results each time, but we don't know a particular value for it, so we can't condition on it. And because it is not something we're conditioning on our background information, then now the trials aren't independent of each other, and we can do inference, right? So when we observe some values, we get some updated probability information that affects our assignments going forward, and so the results of the trials aren't independent anymore, and we can do survey sampling and say, well, at each stage of the game, we have a probability assignment, we have a posterior distribution for the parameter, etc. Okay, so in the end, it might be that our probabilities are going to match the frequencies, and we'll see kind of how that might come about. All right. So let's imagine that we had done this somehow, or we had come up with a working hypothesis that we were going to condition on for what this parameter is. So let's say that we assume that the fixed proportion has a particular value, and let's just call it little p to make it kind of clear the difference here. So if we start conditioning on that assumption of the parameter being a value little p, then we can ask the question, right? Okay, so let's say we do the sample of n people, and we define r as the number of yes votes or yes answers that we get, and f is going to be the ratio of the two, so that's our kind of frequency that we expect that we might observe. Okay, so we might ask the question, what probability would we associate to that frequency? So what probability would we assign to the statement that f has a particular value? Okay, so the way that we would actually summarize that is probably with the probability distribution. Okay, let's write it this way, which we know how to do, right? So the probability of getting, let's say, a value of r over n, so I'll write it again as probability. Sorry, I'm kind of going back and forth here. But This is, as random variables, and this is a particular value. Okay, I hope that's clear enough. So what's the probability that we'll realize a particular ratio of yes votes to total votes, conditional on now this sample and an I, and our assumption of the fixed proportion. Okay, that's what I wanted to write. Okay, so let's write this square brackets to indicate this is a probability of a statement. Okay, so clear enough notation, right? So we're conditioning on the number that we sampled, the proportion of voters in the population that we assume is kind of known to us, and all the other background information we have about that sample. What's the probability that we get a particular fraction? Well, that is just the binomial coefficient thing that we've seen before. So let's assume that we do this kind of sampling with replacement. So we sample a person and we may sample them again, that's okay. So we throw them back in the pool, we sample somebody else. So we get a binomial coefficient, n choose r, we have p to the r and 1 minus p to the n minus r. Okay, so that's our binomial distribution that we derived for sampling with replacement problems. And that basically answers the question of what probability, based on our state of knowledge, would we assign to a possible realized frequency that is what we'll actually measure, okay, what we'll actually observe in the experiment. Okay, if you wanted to kind of narrow that down or get a little bit more particular with it, you could ask questions like, well, what is kind of the mean of that distribution? Okay, so what's the average frequency that we would estimate from our kind of probability distribution over these frequencies? And it turns out that the average of the binomial distribution is just the parameter p. Okay, so if we're scaling things down so that they're on ratios from 0 to 1, the average of that distribution on those fractions is little p. Okay, we might also ask the question, all right, how spread out is that distribution? Right, in the same way that we had kind of posterior probability distributions for parameters, we have now kind of a probability distribution for a realized frequency. And we might ask the question, all right, what's our kind of standard deviation for that distribution over the possible frequencies? So that would be, kind of our average of the squares minus square of the average. And it turns out that that is just the number p times 1 minus p divided by n. Okay, so we've seen this again, I think probably earlier on, but the point here is that if we do, let's say, a large number of trials, and we're conditioning on some assumption of a fixed proportion each time, the realized frequency that we would kind of expect to get, in the kind of average sense, right? The average of that distribution would be p, and the size of that distribution scales with 1 over the square root of n. So this would tell us basically what range of frequencies would we be surprised to get, not surprised to get, how far outside of or away from this mean value of p would we start to associate those events having very low probability, and therefore basically at what point will we start to maybe second guess these assumptions about that population parameter or any of the other assumptions that are embedded in this prior information. Okay, so this is then how the probability assignment might give us a frequency estimate, right, or an idea of what frequencies we would guess at, or what things we would be kind of surprised to see. Okay, we can very easily turn that around, just as kind of we've seen here. If we imagined doing this inference, right, starting with a kind of uniform prior and repeating this experiment multiple times and getting some fraction of results, and then now doing the inference. So the basic kind of template of that, as we've seen before, is, let's say, on this uniform prior, after observing these the sample of size n of which we had r successes or yes votes or whatever it is, we know that our posterior probability assignment for the next person being a yes, so let's just write that as rn plus 1 equals a yes, conditional on this little r and little n, and our background information I, right? That now forward-looking probability for the next polled person giving us a yes vote is what comes about through Laplace's rule of succession, right? So this is what we saw a couple of videos ago. Actually, is the number r plus 1 divided by n plus 2. Okay, where r is our number of successes and n is the number that we did in the sample. Okay, now that you actually kind of see that here. So like after doing no samples, our forward-looking probability is 1/2, so that's a 0 plus 1 over 0 plus 2. If we do one sample and get a 1 yes vote, our posterior probability assignment is 2 theta, and if we take the expectation of that, we're going to get 2/3. So that gives us, that's a 1 plus 1 over 1 plus 2, etc. So the point here is that we have a natural way in which the frequencies that we observed are informing or are dictating our probability assignments for maybe further results of the sample, because we're basically able to do induction and do inferences on the missing parameter that we're not able to condition on. Okay, so Jaynes, I think, talks about one of these or the other in terms of the Poisson distribution for the source detector problem. It's not necessary. I think that the essential point here is that if we have an assumption about, let's say, a parameter that gives us a very fixed probability, right? So our probability model, we're able to just write down the probabilities, and we have some kind of background information that tells us that things will be independent, so we assign independent probabilities to the results. Then we can come up with a frequency distribution that would be the binomial distribution, and we can ask things like, okay, what's our mean frequency? How spread out are the frequencies? What would be our kind of distribution of frequency probabilities, or probabilities of observing frequencies of different numbers. So that's basically all going forwards, asking the question of, from a probability, what frequency estimates would we make? But we can very easily turn that around the way that we've done many times with kind of inferential problems of survey sampling or parameter estimation. So if we started off with a situation where we didn't know the probability, and we started doing some sampling and we observed frequencies of various values, then we have things like Laplace's rule of succession that gives us now the probability that we'd associate to getting a success on the next trial. And that just comes through naturally in our kind of inferential program, where each time we update our probability assignment for the parameter based on what we observe. Okay, so really we've seen, I think, examples of this going either way, where probabilities can become frequencies and frequencies can become probabilities. And the point is, in neither instance are they really the same thing. They can just inform each other based on what other background assumptions we make and the ways in which we're kind of treating the information that's present in a problem. Okay. So, yeah, I think, Jaynes makes some very good points here about the nature of induction, and we don't need to go into too much further detail because I think this kind of captures the essence of it. But really, there's kind of a subtle point here about, all right, what is the purpose of doing these probability assignments and then making inferences based on, say, what we observed? If we can just ask the question, well, okay, given some assumptions, what frequencies would we expect to get? And it'd be tempting, I think, to look at this as saying, okay, well, what frequencies do you expect to get? That could be either right or wrong. And so you either did the probability right or you did it wrong. And I think, Jaynes' point here is that actually probability assignments are not really about being right and wrong, or at least they're not about being right in the sense that people usually think of. So what he basically says here is that we know that induction is a very important part of science because obviously we're frequently dealing in situations where we don't have all the information and we're trying to explore and gather information and make inferences from partial information or situations of uncertainty. And the whole point of probability is not to kind of get the right frequencies coming out of that engine, but really to just say, okay, based on what we currently know, or the working hypothesis that we're making, or our kind of state of information that we currently have, what conclusions are most strongly kind of indicated by that state of knowledge. So basically, what predictions would we make, or can we make based on kind of what we're assuming now? And then that will guide us to doing experiments or testing those predictions by quantitative rules like this one. So we might say, okay, these are the frequencies we might expect to see, and we would be kind of unsurprised to see results that are within some range of that. If we started seeing results out of that range, then we might start questioning this assumption or that assumption, and we might actually get some new knowledge. Okay, so this is the whole point, I think, in Jaynes' description of induction, that it's kind of most useful for a working scientist when it leads you in directions that are actually wrong, right? So when it makes predictions that then disagree with what you observe in the course of doing an experiment, that is kind of wrong in a productive way where you might be able to go back and learn some things about your assumptions or about the constants or the parameters that you felt like you had assumed underlying the experiment. And if you learn something, then that's good, right? You make conclusions and you gather new knowledge, and then you can kind of lead yourself to other experiments. So he kind of describes the history of science as being more about doing induction by making wrong predictions that were wrong in productive ways, where you could do an experiment and then learn something from it and guide you to then what other experiments you might do in the future. Okay, so it's just more a question, I think, of attitude than anything else. But the point here is that probability is just kind of a reflection of what we think we know and don't know, and some of those things might be wrong. Right? So if we're assuming something that's wrong, we want to know about it. We want to find out, and the way we find out is by asking what consequences our assumptions would have, and then testing those consequences. Okay, so that's kind of one side of things, and the second side of things is, all right, if we do these experiments and we are making inferences, what do we learn? Okay, so these are the kind of two essential questions in induction. To see that kind of worked out, I guess, in another way where probabilities and frequencies play off each other, we can generalize this a little bit to talk about situations where we have kind of more than one state and we've got probabilities assigned to all the different states. Okay, so here we're assuming kind of just successes and failures. But if we generalize that to, let's say, we have hypotheses, okay, a sort of universe of possible hypotheses can give us different probabilities for the different states. Okay, so let me write this this way. So our hypotheses will all have the kind of form of saying the probability of getting a particular result on the ith, or sorry, on the ith iteration of the experiment, getting result J is going to be some probability, let's say Pj, and we're going to assume that the results are independent of each other. So actually, let me write this a little bit more generally. So let's say our probability assignment to getting, let's say, a vector, let's write it this way, x1 x2 to xn, so this is a particular outcome. This is the way I want to write it. Our probability assignment for that outcome of the experiment, conditional on this working hypothesis, is always going to be just probabilities associated to each one of these results, but multiplied up because we're going to always have independence of the trials. Okay, so this is what Jaynes calls the Bernoulli class. Okay, Bernoulli class, which just means different probability assignments for the different results. And so the way that will play out is we'll have maybe some number p1 that's associated to result number 1, result of type 1, and we're going to have that multiplied up however many times we observe result 1 in the outcome. So that's going to be to the power n1, we'll call it n1, and then times a probability p2 to the power n2, etc. Okay, so in the end we might have m of these probabilities, and we're going to be raising them to powers that depend on the number of times they're observed in the outcome. So let's just kind of keep track of that maybe over here. Okay, so these x1 through xn are the results of all the individual trials. Our kind of outcome states are labeled 1 through little m, so those are our possible states that we can get. The names of those are, let's just say they're 1 through m. We have probabilities associated to them, which are like p1, p2 through pm. Okay, that's coming from our working hypothesis in this Bernoulli class. And then we have what's called the sample number, which is the number of times it occurs in the outcome. Okay, so the number of experiments that terminated with that state, 1 through m. And our assumption here is that the sum of these things is going to be n. So we're doing a total of n trials, and whatever these sample numbers are, they have to add up to n. So anyway, any hypothesis that has probabilities in this form, we're gonna call that a member of the Bernoulli class. Okay, we've seen this before, I think, a little bit. So the question might be, all right, if you did the experiment then, right? So you did n trials and you got various sample numbers, etc. What would be your kind of inference in support of one of these hypotheses or another? Okay, so let's say that you you did the experiment and you want to ask the question like, what is our evidence? Say, write it this way, for the hypothesis conditional on a particular realization, x1 through xn, and our background information. And in particular, how does that move relative to our kind of prior evidence? So this is, again, evidence on the log odds scale, the way that we've seen it before. And let's just assume that we're doing this kind of in the context of a binary hypothesis test. So we're testing one of these hypotheses against another one. So let's just write that in here. If we have, let's say, 2 such hypotheses, which we'll call h and h prime, and we make the assumption that they're mutually exclusive and exhaustive. Okay, so it must be either h or h prime. What kind of evidence do we get for our chosen hypothesis h as a result of doing that sample? Well, and getting these sample numbers. When we did binary hypothesis testing, we actually worked this out and saw that we could write this difference as something like 10 times the log of the probability ratio, which is the ratio of these 2 probabilities, sort of data likelihood under h, okay, divided by data likelihood under h bar. Okay, so hopefully this is familiar to you. This is just restating the kind of product rule in the case of the binary hypothesis. So we take, we'd have a total probability for the data ordinarily for h, not conditional on h and not conditional on h prime, but then we divide those two by each other. The total probability cancels, and we just get data likelihoods for h and h prime. Then we take the log of it, multiply it by 10 to put it on our kind of decibel scale. Okay, anyway, that's the change in our evidence for the hypothesis based on observing the data. Okay, so something kind of interesting happens if you actually play that out and look at what happens for probabilities that you can write in this particular way. And I'll just kind of do a little bit of this because I think it's kind of cool. So, okay, again, substituting what we have in here, probability for H is going to be kind of P1 to the N1 up to Pm to the Nm. P1, let's say P1 prime for the H prime hypothesis to Pm prime to the Nm. Okay. If we say we want to write these things kind of relative to the observed frequencies that we got, okay, then it helps if we actually kind of throw in there some factors that will sort of multiply and divide by those frequencies. Okay, so let's just give a name to these things, and let's call the frequencies just the relative proportions of each one of these things. So maybe F1, which is N1 divided by N, up to Fm, which would be Nm divided by N. Okay, so that's just the sample numbers divided by the total. The sum of those things would be 1. Okay, so let's say that we kind of throw in some multiplying and dividing by those things just to kind of express these probabilities relative to those frequencies. And it's going to look a little bit weird, but hopefully this will kind of make sense. So if we do, let's say 10 log 10, let's write it as, let me write the next line actually. So let's write this as 10 of f1 to the n1 times f1 fm to the nm, okay, divided by this denominator term here, p1 prime to the n1 dot 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 pm prime to the nm. Okay, so we've multiplied by this thing, we have to divide by it. Okay, no big deal. Okay, and then we have in our numerator still p1 to the n1 pm to the nm. Okay, log of that whole thing. All right, now let's start grouping together some of these fractions. So that would be, let's write this over here, 10. We have f1 over p1 prime to the n1, fm over pm prime to the nm, times, right here, this might get a little squished, but hopefully it's okay, f1 divided by p1 to the n1, okay, hope you can see that, times dot 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 fm divided by pm to the nm, and all of that is going to be the reciprocal. We have to take 1 over that, minus 1 power. All that's in the log. Okay, still kind of working this through, but might start to kind of look suggestive here. So we have a log of a product of things, so we can write that in terms of the sum of the logs. Okay, that's kind of what we're aiming for. So we have log of the product of these things, so let's take the sum of the logs of them. So the log of each one of these things is now log of something to an exponent. So that's going to be like the sum of, let's write it as nj, log of fj divided by pj prime. Okay, so far so good. Hopefully you see that. That's going to be our sum from j equals 1 to m. And now we're going to have minus something similar because we have a log of something to the minus 1. So we have a minus, let's just write it as 10 log 10 sum. We have nj terms, and we have log of fj divided by pj. Okay, so this was the whole kind of point of writing in this way, that we have basically this nice kind of looking expression that depends on the pj primes, and then we have a nice similar, exactly the same kind of expression with pj in there. Okay, and actually we can make this look even a little bit more suggestive if we multiply and divide by n. Okay, so nj we said is, the frequency is nj divided by n. So let's write n out front and make that, instead of nj, it's going to be fj. Okay, so nj we're writing as n times fj. Similarly over here, so let's put an n out in front, and we have fj inside. Okay, just the realized frequency. And so what's interesting about this is that this quantity here, this sum quantity, okay, so 10 log 10 times n, sorry, n obviously goes outside the log, 10n log 10, that's what I mean to say, 10n log base 10 of that. Okay, this quantity, sorry, there's no log here. Log's inside. Okay, Aubrey, get it together. All right. Third time. 10n times that sum of logs. That's what I mean there. Okay. Anyway, the sum here, okay, forgetting about the 10n part, but the sum of fj log of this ratio has actually it's a famous quantity, and it's known as what's called the relative entropy, or the Kullback-Leibler divergence. And it's the Kullback-Leibler divergence of the frequencies from the probabilities. Okay, so the reason that that's interesting is that it's kind of a handy way of just sort of summarizing, the evidence that we get from this frequency observation. But another way to see it is that, or kind of something else to observe here, is that we're talking about testing a hypothesis against another hypothesis. Well, what's the best that we could possibly do? The best that we could possibly do would be the hypothesis H prime, where these two things are exactly matched. Right? Our probability predictions are exactly equal to the realized frequencies, in which case this ratio is going to be 1, the log is going to be 0, and our sum is just going to be 0. So if we, just go up here. So if we kind of imagine that, we had one hypothesis in mind, and we were testing against this kind of ideal H prime with, probabilities equal to the realized frequencies, so kind of the best possible H prime we could get, well, what would that do? So basically we'd have a 0 term here, and we'd have evidence based on, the observed data, the observed frequencies, minus whatever prior evidence we had for this hypothesis, equals this minus, term with a constant up front, times n times this, let's just call it d for this Kullback-Leibler divergence. So the point is, as n grows, this evidence, which is against h, right, it kind of scales with n linearly by a factor that depends on basically how different the frequencies and the probabilities are from each other. Okay, so this is the kind of essence of this relative entropy term, and we don't need to think about it too much, but just kind of plant it in your mind that it's a handy way of summarizing a kind of distance from one distribution to another, where once you have it, in this hypothesis testing example anyway, the evidence for a hypothesis in the Bernoulli class, kind of tested against the best possible one, that evidence just kind of scales linearly with the number of samples. So if, let's say, this distance were very large, or were kind of substantial, then after some number of samples, you might say, okay, we've got lots of evidence against H. Or, another kind of extreme might be, well, maybe the distance isn't so great, but there's some kind of divergence there, and after a large number of samples, that adds up to actually some significant evidence against that hypothesis that led you to those probabilities. Okay, so this is just kind of playing out in kind of for the m possible sample situation, the same kind of thing we had before with inferences about a single probability. But the point is that the frequencies that we observe are playing a very key role in the course of that inference. Okay, and what they're telling us is basically the kind of incremental evidence we get per sample, so kind of per each value of n that we sample, the incremental amount of evidence that adds up to as evidence against whatever probability assignments we made, and in favor of maybe a different set of probability assignments that more match the observed frequencies. Okay, so it's another kind of subtle way that probabilities and frequencies will interact with each other when we restrict ourselves maybe to a set of models in this Bernoulli class. Okay, so there's one other kind of version of this then that Jaynes considers and I want to get into, which is what else we might condition on in the poorly informed robot. Okay, so basically what other kinds of information we might give this robot to reason about, and then ask the question of, right, what inferences would it make? So what kinds of conditional probabilities would it draw? So this gets actually very kind of interesting. And it's the start of something much bigger that will come up later in the book. But let's just imagine that we start with the poorly informed robot and we condition it on other information like this kind of information we had here. So let's say we condition on the sample numbers, meaning the number of instances of the experiment ending in one of these m states, n1 through nm. Okay, and we ask the question, what would the robot say is the probability for, let's say, r1 equals 1. Okay, so it'll be a similar kind of thing for any one, but let's just start there. So we know that that probability is going to have to do with the multiplicity of this event, but now conditioned on some restricted universe of situations where we have particular sample numbers. Okay, so what we're going to need to know is the multiplicity of this event and of events like this. So let's start with, as we kind of work our way up to this, let's start with the question, what's the probability of getting a particular set of sample numbers? Okay, so that's going to be kind of the denominator term in our probability assignment, conditional probability assignment. So what is that probability? Well, it's going to depend on the multiplicity. Let's say the multiplicity of these, how many ways we can get these sample numbers, which actually turns out to be a fairly nice number to compute, called the multinomial coefficient. Okay, so it's going to be a number we'll call W that depends on what sample numbers we're talking about. Okay, and actually the formula for it, it's very easy to write down. It's n factorial divided by n1 factorial, n2 factorial, etc. nm factorial. Okay, now why it's this, you could basically see this from, this is like a generalization of the binomial coefficient. Okay, so if we're talking about getting a sample of size n1 and n2 in two possible states, we know that the number of ways of doing that is like n choose n1, which would have n1 factorial, n minus n1 factorial. Okay, for multiple possible states, you basically can build that up as the number of ways of choosing the n1 out of n, and then the number of ways of choosing n2 out of the remaining ones. And if you write out those products of the binomial coefficients, you get nice cancellation, and you end up with just this, what's called the multinomial coefficient. Okay, so far so good. So the point is, or the question is, all right, so that's our probabilities kind of in the denominator term. What's the probability of getting, let's say, R1 equals 1? conditional on these things, well, that's going to come out to be basically the multinomial coefficient with an R1 that's restricted. So what do we have left? We have n1 minus 1 counts of result of type 1. Okay, so remember, n1 is the number of times that the 1 result comes up. If we assume that one of them happens first, then we have a remaining number n1 minus 1, okay, up to nm. And in our denominator, we're going to have this multiplicity of, all of the possible ways of getting those sample numbers. Okay, so if you do that out, you put in n1 minus 1 factorial here. The total here is n minus 1 factorial, so that's what's going to go on the numerator. Anyway, what you'll see is that everything cancels, and you just get n1 divided by n. Okay, not too earth-shattering, but interesting to see. So this is just kind of a combinatorial result that if we start with all of the possible m to the n outcomes, and we condition on having particular sample numbers, basically particular numbers of each one coming up a certain number of times, we still don't know anything about the order, right? So this is kind of the essence of it. So we know that we got result 1 n1 times. We don't know where those n1 times were. So the probability of the first trial being one of them is basically the number of that n1 number of 1 results divided by the total. Okay, so this is, you can think of this like as an urn drawing problem where we know the proportions, but we don't know the order that they come out in. Okay, not too surprising. Okay, but let's now think about other kinds of information, and this is where things are going to get a little bit more interesting. So, let me leave this up here. So let's imagine, instead of conditioning on the sample numbers, let's associate a value to each possible state that comes out. Okay, so these are labels. Let's say maybe in addition to labeling the states, we associate some value to them. Okay, and the value we'll call G1 through Gm. So this could be like the amount of money that you win if state J comes up, or whatever it is. So now, instead of conditioning on the actual sample numbers, let's see what happens if we condition on the total G, which we'll define as the kind of sum total over the experiments of all the values, or if you kind of break that down in terms of the sample in terms of the labels, this would be J equals 1 to m, it would be the value of getting state J times the number of times you got it in the experiments. Okay, so hopefully that makes sense. So Nj is the number of results that we got of type J. Gj is the value associated to each one of those. So our total value for the n trials of the experiment is just this sum broken down by each of the m labels, number of times of that one, times the value of each one. Okay, if we do that conditioning now, something very interesting happens where we no longer know exactly which sample numbers we're dealing with, but we can kind of start to say some meaningful things. So in particular, we know that we're going to need the multiplicity, okay, which we'll write multiplicity of getting this event G. So basically number of ways of writing out a sequence of results that have this kind of sum total value equals capital G. Well, that's going to be a sum over some possible sample numbers, which we'll write n1 through nm. Okay, that sum of the multiplicities for each one of these sample numbers. Okay, so first we have to pick a collection of sample numbers. The multiplicity for that collection of sample numbers is what's shown here, right? So that's this multinomial coefficient. Now we only add up over the sample numbers that satisfy this constraint that we're interested in. So well, let's just say that this is ordered n tuples or m tuples of sample numbers in some set R, where R is the set of possible sample numbers that satisfy this constraint. Okay, I know we're getting kind of heavy with the notation here, but hopefully this makes sense. So basically we're saying, all right, we're interested in the number of possible sequences of results we can get that satisfy this constraint, where our sum total value equals g. We can write that in terms of the sample numbers, the number of occurrences of each result of each different type. If we pick one of those kind of sample number vectors, right, that actually satisfy that constraint, we know the number of sequences that correspond to that sample number selection, and it's just the multinomial coefficient. So we've got to add all these things up. Okay, so these are our set of all acceptable sample numbers, and these are number of sequences for each one, and so we add up overall that whole set, and that's going to be the multiplicity of this event G. All right. Now what's interesting about that, that Jaynes shows, let's just write this. So if you look at this sum, okay, of these multinomial coefficients over all possible sample numbers satisfying a constraint, it turns out that this sum is dominated, okay, it's kind of entirely attributable by one term. Okay, this is the kind of miraculous revelation. So basically the way to think about this, and we don't need to go through all the details in the video, but the way that you can kind of see this is that the multinomial coefficient, which I wrote here, it grows so quickly in n that depending on the choices you make for these n1 through nm, you might get very, very large numbers or numbers that are much, much less. So basically there's one kind of optimal choice for the n1 through nm. Okay, I'll just write it this way. There's an optimal choice, say n1 star through nm star, that gives you the maximum value for this multinomial coefficient, right, for a given n. And it happens that when you do that, it's so much bigger than all the other terms in this series that no matter how big this constraint set is, however many sample numbers are kind of allowable, that single term is going to dominate this sum, and you're going to get basically that this multiplicity of n, the multiplicity of this event G is just this kind of W max, okay, this W of this particular choice of sample numbers, n1 through nm star. Okay, now how do you see that? Well, again, it doesn't matter too much, but what is kind of interesting to do, just by way of approximation, I do want to write this out, is if we think about these multinomial coefficients and how they scale with n, let's write this in terms of the frequencies. Okay, so again, this is n factorial divided by, let's write all these as n times some frequency factorial, just to kind of put things back on frequency terms. Okay. It happens that for kind of in the scaling regime that we're talking about here, we can approximate n factorial very well as n to the n over e to the nth power. Okay, this is Stirling's formula approximation, kind of just the first order term of it, which is all that matters. Okay, if we do that kind of approximation, okay, just maybe have to take my word for that. Sort of substitute that in, what do we get? Well, n to the n, or n factorial, we're going to say that that's about n over e to the nth power. And then in the denominator term, we're going to have like n f1 over e to the n f1 power. Okay, that's just that thing in the Stirling's formula approximation times dot 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 nfm over e to the nfm power. Okay, roughly speaking, that's kind of how it scales. We can pull out a bunch of terms of that. So top we have n over e to the nth power. In the denominator, in each one of these terms, we have an n over e to some power. So we can write that as n over e. And then we're going to have n f1, n f2, dot, 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 n fm. So if we kind of group together those terms, it'll be like n f1 through fm in a sum. Okay, and then we have terms left over like f1 to the nf1 dot 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 fm to the nfm. Okay, again, a little bit of a hairy calculation, but hopefully this is kind of, you can see at least the steps that would get you from one to the other. So we're sort of we're pulling out the n over e terms from each one of these terms in the denominator, and we have exponents like that have an n in each one, and we have a common factor here of f1 plus fm. Now, by assumption, right, these frequencies were just the relative proportions of the sample number, so this is the point. They add up to 1, right, by definition, and then these two terms cancel, okay, lo and behold. So what we are left with in the end, let's just go here, is that the, let's say, the multiplicity for this particular kind of maximizing value that we're interested in, if we, right here, it's just going to be 1 over frequencies to their n times their powers, okay, like that, n times frequency. Or if we kind of take this in log terms, and we want to know how is this kind of scaling with n, when we take the log of it, so 1 over n log of w, what's that going to be? Well, the log of this thing is minus the sum of the logs of these things. Right? The log of each one of these is going to have an n term in the front. And then we have an f1, and we have log of f1, or fj, log of fj, and we're taking that sum, j equals 1 to n. Okay? Right. So that's the log of it. Now we have 1 over n of that, so the 1 over n cancels the n. That's what I wanted to get to. All right, so basically this is saying that this multiplicity term, which we determined is kind of the only thing that matters in this final sum of multiplicities of all these sequences given a sum total value, the maximum value of that, the kind of single one of it, scales like e to the n times some constant, which we'll call h, and that constant h is here. Okay, so h is the thing that is 1 over n times the log of w max, and it's just the sum of frequencies times the log of the frequencies for this particular choice of frequencies that somehow maximize this multiplicity subject to the constraint that we had written down earlier. Okay, so we'll come back to this later in the book, but basically what we see here, this term h, hopefully you can kind of see how this is similar to what we were talking about in the same spot over here with the Kullback-Leibler divergence. This is called the entropy. Entropy of this frequency distribution. And the way to kind of say this in words is that if we condition on the sum total value of this kind of function, or this value that's associated to the different states, okay, conditioning on it is the same as conditioning on its average. I guess I didn't write this, but let me say this here. So conditional on G, which is the same as conditioning on G over N, right? Which is the average of G, or you can write this as maybe the average over the frequency distribution. Okay. So just dividing through by N, conditioning on that kind of weighted average value gives you a probability assignment, or it gives you a multiplicity that only depends on the frequency distribution that maximizes the entropy given that constraint. Okay, so another way to think about this is that if we want to know the question of, what sample numbers might we get that come up with a certain value. So let's say that we're talking about dice rolling, and we have 6 possible states, and let's say we assign the value of j to state j. Okay, so the die coming up 1 we'll say is a value of 1, etc. If we then conditioned on, let's say, the average dice roll coming up in some large number of trials being 3. Okay, so ordinarily we'd expect it to be 3.5, but let's just say that we don't really know about kind of the mechanisms of this die, and so we condition on the assumption that it's going to come up 3 kind of on average over some large number of trials. Well, there's many different ways that could happen, right? It could happen that it's 3 every time, right? So we have kind of sample numbers of all zeros except for n 3s, so maybe n is 1,000. Or it could happen that we have kind of equal numbers of 2s and 4s, or equal numbers of 1, 2, and 4 and 5, right? All of those things together would average up to be 3. And the point that's being expressed here is that there's kind of one particular choice of sample numbers, meaning frequencies of the different results, that gives you so many possible ways, so many possible sequences corresponding to that sample number. It's so much more than any other choice of sample numbers, that basically, for all intents and purposes, you can say with probability 1, you have that choice of sample numbers. Okay, so like in the example I was just saying, the possibility that we have 1,000 3s in a row, since there's only one way you can write that sequence, it's very, very improbable, starting from this position where all the possible sequences are equally likely. Whereas, sequences that have kind of equal numbers of 2s and 1s and 4s and 5s, those sequences are going to have a lot more possible ways of writing them out, a much higher multiplicity, so they're going to have a much higher probability. And actually, in the end, what you'll see is that there's a single term, a single sample count choice that so dominates that sum that we can say conditionally that our probability is near 1, we're nearly certain that we have that sample count. And that sample count comes from what's called the maximum entropy consideration. So we find the frequencies by maximizing this entropy term here, which is just the sum of f times log f. Okay, so again, we don't have to go into it now, and it's something that will take some time to play out later in the book. But basically, what we have here is the beginning of Jaynes's maximum entropy school of probability. So Jaynes, one of the things that he's known for, in this book, is introducing this idea that if you're given basically a first order constraint, like an average, a weighted average over some probability distribution, the kind of most ignorant possible distribution you can make is the one that maximizes entropy subject to that constraint. Okay, and then that thing is going to determine all the probabilities that you calculate from it. So we see a little bit of the argument here, and again, that's going to get played out later. The big question is going to be, how do you find this maximum entropy distribution? It turns out to be a non-trivial problem, and that is the subject for a later chapter in the book.